few things out of the way. I want to, first, one thing that I want to know is that some idea about the audience, because I am not very sure about the, uh, about the how I can't even see the audience, right?
Yes, you
So,
can't see.
the audience are mostly students, or are they professors?
No, they are mostly students, and they are, you can see majority of masters and PhD students. uh, so
Okay.
there are maybe I think couple of, I don't know, maybe one or two could be BTech students, but they are like graduate students. Hmm? And
Okay. Okay.
mostly with either they are working with me or Somya.
Okay. All right. Sure. Sure. Okay. So I'll try to explain with that in mind.
Uh,
And the other thing is that so the content of this work I'll explain is a very recent research that one of my students, Aditya Chaudhary, you can see his name on the first page. He did with me, and he just now finished. So so this is this the problem, of course, is very well known, and I'm sure that many of you have either worked on it or you know about this problem. But nonetheless, the techniques that we use and the results that we have all are extremely new, and many of them are untested also. So there might be errors, and also it might not be fully threshed out. So I would encourage questions in the middle, especially since that you most of you are students. Please ask questions in the middle. I expect the main talk to last about 1.5 hours. So I'll split it into 2 days, like we discussed, and that gives us some leeway in terms of questions also. So if you want to ask questions in the middle, please do ask. Don't wait. Don't have to raise hands. Anyway, we have only a very few people here, so I think you can directly ask without waiting for me to stop or anything. Just ask if there are any issues. Okay. So I hope all of you can see my screen. And if you're not used to this format, what you should do is that you should pin my video so that it is full screen for you, so that you can see what I'm talking about, and also any writing that I do on the screen. I'll do extensive writing and pictures on the screen. So please pin my screen so that it is full screen. Okay.
just Professor Devraj, I want to say maybe people have heard about this, but they don't have a background. So if you want to take your time, it's no issue.
Okay, all right,
Mm,
sure. I don't have too much background slides,
mm,
but I will try to go slow in the initial part.
mm,
So one good thing about this technique that we are going to use is that it is unrelated to
mm,
most of the classical stuff that is there in the area.
mm,
So as a result, you don't really need to know. But if you do know, of course, you can compare
mm,
and judge for yourself the advantages and disadvantages of this method of going into this problem. But yeah, let me at least introduce the problem first, and let's see and take it from there, depending on your questions. So I don't remember what exactly topic I had sent, so I called it new results for the game of two cars. How new, of course, is still to be judged. Yeah, we'll see. So game of two cars. It's of course I say cars, and then I draw aeroplanes here. So you might not like it. So if you don't like these aeroplanes over here, you can replace them with cars. The idea is that these aeroplanes or cars or whatever vehicles you have here, they have some direction in which they can travel forward, and they can turn also like this. But there is a minimum turning radius circle. Means what? That it cannot turn like this. So this is not allowed. But any turn like this is allowed, turn like this is allowed, like this is allowed, up to this point. Yeah, up to this sort of a turn is allowed for these vehicles, whatever they are. Aeroplanes, of course, travel in three-dimensional space, but we will restrict ourselves to cars only. In reality, all the math that we'll do are for cars only. Means that it is going to, everything is going to work out on a xy plane. A planar game is what we're going to play. All right. So fine. So now game of two cars, very roughly speaking, is what? That we have two such vehicles, aeroplanes or not, which has this sort of a turning constraint. And of course, there is another constraint on how fast it can go forward in these directions. And this one is also like this. It can go like this, it can go like this, it can go like this, and so on up to this minimum turning radius circle. So up to this point, these two vehicles are identical or not, we'll discuss later. But the objective is that one of them is a pursuer Yeah, and the other one is a evader. So I'm assuming that you are you have some idea about this pursuit evasion time games type games. Means what? That the pursuer is supposed to come, and catch the evader, and the objective pursuer's aim over here is that this is like a time to go game. The one that we'll be talking about is a time to go game, means, or a minimum time game, means that the pursuer is going to try and capture the evader in minimum time, and the evader is going to try to avoid this capture for as long as possible. Okay, so this is the basic setup for the game of two cars. And you might know that this is like a very old classical problem introduced by this person, Isaacs. In this is initially it was in 1952, 58, and 59. It used to be a Rand Corporation report. Then it came out as a book, this thing called Differential Games. And from that point onward, this has been one of the this book has been one of the main references in this area, and a lot of work has gone into understanding and further solving many of the games that he proposed. So this is one of the games that he proposed in his book, and this is called a game of two cars. And we also call this sort of vehicles which are which have a minimum turning radius, we also have another name for them. These are called Dubin's vehicles. Yeah, so Dubin's vehicles or Dubin's cars are also a common name for this, because of a reason, because Dubin studied individually such vehicles before Isaacs talked about the game of two cars. So essentially we'll be looking at this game, this specific game, and this game is also quite complicated and it has many ramifications in various directions. We'll be talking about a very specific case for this game. Okay, so right, Tushar, you might want to mute yourself unless you want to say something. Thanks. So Dubin's vehicle now, so I'll explain now, because Professor Kothari said that you might not be knowing this very well. So here is the here are the equations, the kinematic equations for this Dubin's vehicle. Of course, one might say that, look, a real car will have dynamics also, it will have some mass and so on. But to simplify things, we are going to look at only this kinematic equations, no dynamics at all. So, and this has this equation, so x dot, so this is the x position. So here when we look at this position, so this is the x position, this is the x, this is the y, this is the theta, and the equations are related like this. There is a forward velocity v, x dot is v cos theta, y dot is v sine theta, and theta dot is v times omega. So when you look at this problem from a point of view of control, you have two control variables. What are the control variables? One is this v, how fast you want to go forward, and what is the rate at which you want to change this theta. So theta dot is proportional to omega or wt. So this wt is something that you want to control. The control inputs are ut and wt, both of them. So in various formulations of this game, some people will assume this ut as constant.
Excuse me, sir. I have one doubt.
Yes. Go ahead.
This theta dot and theta dot equal to v omega t.
Yeah.
Does it unit matches on both the side?
You can
Because
normalize.
theta dot
Yes,
is radian per second.
yes,
and
yes. You can put appropriate constants to match. Yes, this is just for everything is uniformly taken in terms of some what do you call it, normalized units. So yes, you are right. We should sometimes people put a r over here to match this, but that's okay. I mean, either way, for mathematical purposes, both are fine. This is also
okay.
But yeah, you are right. To make it, if we take like normal units, this will not match. We require another constant to get this to what you want. Right.
Okay.
So that's correct.
Thank you.
But but you see, the trick over here is to have this v over here or not. So some formulations of this game will also have theta dot equal to just omega t. Yeah. So I mean, of course, modulo some constants like you want. You can put whatever constants you want. So theta dot equal to omega, this equation tells you that you can change this theta even if there is no velocity. So this is sometimes a problem. To avoid this, we have this v over here. What this says is that, look, you cannot go into, so this radius of curvature, whatever radius of curvature we're talking about, So you cannot go into this even if you decrease the velocity. So this simplifies the game somewhat. So if you are used to this sort of games, you might notice that this v is multiplied. In some formulations, in Isaac's formulation, this v is over here only with some constant. But in other formulations, theta dot equal to omega is also assumed. So we don't assume that. Okay. So we don't take care of this issue over here. We're talking about this one. So just to clarify. So right. So this is the coordinate frame. And now here we are just going to explain what happens. So this two inputs, remember, one was v and other was this w or omega. So we're going to assume that this wt is limited within some plus wm and minus wm. So it can go in both directions. Means that it can go like this, it can go like this also, both ways. And v is limited to 0 to vm. Okay. So of course you have this other car, this game of two cars. This is Dubin's car. And there is this other car also which allows motion in the backward direction also. So that also we do not treat. So I'm going to sort of slowly one by one get rid of many assumptions that will simplify stuff for me in the end, equations for me. So as you can see, slowly I'm going there. So one is that I cannot go backward, I can only go forward. Minimum turning radius, even if I go slow, I cannot go into this circle directly. Yeah, these two minimum radius turning circles, I cannot go into that directly. So here is a further picture of left anti-clockwise circle. If you, so this sign, of course, you don't need to remember, but we have some convention. So it is plus omega, then you make this circle on the left. And if it is minus omega, you make this circle on the right. Okay. So this is straightforward. So the radius, this radius that I have here is 1 by omega. So this radius at which I'm turning, the radius of curvature, radius is 1 by omega. So what happens here is that if I put a limit, of course, this is also straightforward, that if we don't put any omega at all, omega or w, I am again saying omega instead of w, please excuse me. But this w, if I put equal to 0, then I put some v, then it goes in a straight line. It doesn't turn at all. Okay. So now, right. So now this, remember, I had assumed here that this omega or w that I have is limited by these two quantities, right? Wm and minus wm. So in that case, it puts a limit on what is the minimum, okay, here, yeah, minimum turning radius. So like I said, this is now directly visible from the math that I cannot go into this circle. The minimum turning radius that I can achieve is limited by the maximum w, or wt was less than equal to omega wm less than equal to minus wm, right? So it is limited by this maximum wm or this wm, the maximum value of w that is allowed by this equation. All right. So the minimum turning radius circle is defined this way by the maximum value of the w that is allowed, and that we assume to be wm. Okay. So the turning radius, if you want to talk in terms of turning radius, the turning radius need to be greater than 1 by wm. Okay. So like I said, this is allowed. So a circle like this, of course, is allowed, but a circle smaller than this is not allowed. Okay. So this is very important. Okay. So now the game of two cars, like I said, involves two such vehicles. One is a evader, one is a pursuer, and both of them have almost the same kinematic equations. But of course, the VP, the forward velocity that you are going to put for the pursuer, and the forward velocity that you're going to put for the evader, the rate of turn that you put for the pursuer and the rate of turn that you put for the evader, these two are potentially different, because they might choose to do different things to save themselves or to catch them as soon as it's possible. So these two are only different in that respect, these two equations. Right. So the game of two cars. Now I want this guy to do what? I want this guy to come. Suppose this guy takes some trajectory like this. So I want this guy, the pursuer, to come and catch him. So catching means what in this respect? So in the traditional game of two cars formulation, catching or capture might mean that the two vehicles that we have, so suppose one vehicle is here, other vehicle is here, pointed this way, pointed this way. As soon as these two come, the distance between these two come to less than equal to some L, you assume there is capture. But in our case, what we assume is that we want exact matching of the coordinates. So xp equal to xe, yp equal to ye is our definition of capture. So you might say this is not really required. I agree, but this assumption lets us make some mathematical simplification, which lets us use a lot of geometry, which would not be possible if I allow this distance criteria. So this one we do not use. This one we do not use. So of course, other people also have used such a criteria before us, but the practicality of the two can be debated. One, you can judge yourself at the end of the talk. Okay. So now the game of two cars. Okay, before I go into this min-max formulation, is the setup okay? Do you understand the setup? Anybody who doesn't understand the setup itself? So one thing I did not say here, sorry, just hold on to that. If you're going to ask something, just hold on to that question. One is that suppose, okay, so this is capture. I want to get this guy to capture the evader at this point or any other point. So now we have to put some assumptions on this pursuer kinematics and the evader kinematics, right? This guy has written dynamics here, okay, kinematics. So what are the assumptions? So the thing is that depending on the capabilities of the pursuer and depending on the capabilities of the evader, you can have various versions of this game. So means what? That suppose this pursuer is faster, but it can turn slowly only. Means what? That the circles are very big, but it is very fast. Whereas this one is slower, but it can turn very fast. So in that case, you can have a game and you can try to find out whether capture is possible or not. In other situations, it might be that this turning radius is very quick, but the speed with which it can move forward is not too fast. In that, on the other hand, this one might have some asymmetry. This one might be very fast, whereas this one turns slowly. So in that case, whether capture is possible or not, that might be a valid question. So all such combinations of the two control variables that we have, so this omega m that we have, and we'll put some limits, I guess, on this. So each of this two control variables, Vp and Wp here and here Ve and We, what are the limits of these variables will determine what sort of game is going to get played. And not only that, whether capture is at all possible or not. So we look at the simplest possible case. In fact, it is so simple that in the classical framework, this might look, very trivial in all respects. But nonetheless, our objective was somewhat different. I'll come to that in a while. So here, what we assume is that the pursuer is completely superior. Means what? That the maximum forward velocity also is bigger for the pursuer, and the pursuer can also turn faster than the evader. If we assume these two things, that the pursuer is superior, so pursuer is superior in all respects. So if we assume this one and this one, then it is shown, it is already known that capture is inevitable. So capture will happen no matter where you start. So that is already known. So if that is the case, we don't have to really go and look for the solution to the what is known as the game of kind. So game of kind and game of degree. These are names given by Isaacs. So game of kind, very roughly speaking, game of kind try to answer the question that what are the initial conditions from which capture is possible, and game of degree tries to then calculate what are the optimal curves with which capture is going to happen, right? So game of kind in this case is sort of is a no-brainer. You don't really require to solve the game of kind because it has been shown already very easily. It's not even something to show that if the pursuer is superior in all respects, capture is inevitable. So capture is going to happen for sure in our setup, even if our capture criteria is very strict that we require exact coincidence of the pursuer and evader. Even in that situation, capture is inevitable. So we don't have a problem with whether capture is possible or not. That question does not even arise. Okay, so then what are we looking for? So in that case, game of kind is solved. So people who have looked at this problem in the classical sense might ask, so then what exactly are you looking for in this? So we already know that capture is going to happen, and the classical techniques proposed by Isaacs and further modified by some of these other, I'll tell in a while. So those guys techniques should work fine over here, right? So let me sort of come to that slowly. So
Professor
Yeah.
Devra, I have a question.
yes,
Just a simple. It's open domain, right? The game is being played in open domain, right?
yes, open domain,
Okay.
no closed boundaries.
No.
So everything is very simple. All the simplifying assumptions have been made, and capture is going to happen for sure. All that is fine, but you see, yeah. Sorry, Professor Kothari, you had some other question.
No, that's it.
Yeah. So in that sort of a situation, what is it that we are looking for? So you see, what is the pursuer's problem? If you look at it from a game theory perspective, let me keep the suspense for a little bit while longer. That what is it that we are looking for? So game of two cards may, what is the pursuer's problem? The pursuer's problem is that I want to capture that evader in minimum time possible, but the evader is going to maximize that time. So this is a typical min max formulation, right? So let's say T, this T we denote universally as the time to capture. Okay. So this T, the pursuer is going to min max the T. So I am going to assume that most of you understand this min max formulation, right? Is that fine? I'm going to ask some random guy. Okay. So Milind, can you verify?
Yes, it's fine. Fine.
Okay. Okay. So this min max formulation is standard because you see the pursuer is going to sort of assume that the other guy evader is going to play the worst strategy for him. So this is like the maximum. He's going to do his best to maximize the time, and the pursuer is going to choose the minimum among those worst case times, and vice versa with the evader. So min max time for him, max min time for him. But you see, what we want is this thing, right? So what is this? This is the feedback policy. So we want to find out what is the feedback policy for the pursuer. So feedback policy means what? Feedback policy means that at any moment the pursuer can assume, we can assume that the pursuer knows the x e, y e, and theta e, and also x p, y p, and theta p. But based on these 6 values, I am supposed to find out what is the best feedback policy that I should use. And not only that, I mean, these policies, the feedback policies we are looking for, I look for the feedback policy of the pursuer, I look for the max min feedback policy for the evader, and I want to be able to compute them in real time. Okay. So I want to find out the optimal policies, mathematically optimal policies, but I want to be able to compute them in real time also. So I don't want to, okay, let me come to that in a while. So this is the objective of this entire work, that very simplifying assumptions in all respects, but the computation at the end of the day, the computation should be so simple that actual implementable feedback solution should be there. Okay. So I'm just not very sure how much you know about the background and how this is solved, but a little bit more before we come to that. So a game of two cards. So this is the Nash equilibrium condition. Means what? The time to go, the time to capture with optimal policies, optimal feedback policies for the pursuer, optimal feedback policies for the evader, denoted by the stars. So the time to go for this obeys this inequality. Means what? That look at this. So suppose gamma p star is the optimal feedback policy for the pursuer. Gamma p star here also is the optimal feedback policy for the pursuer. So if evader also played optimally, you would have got this value. Yeah, T of gamma p gamma e star. But on the other hand, if the evader chooses to play something non-optimal, anything other than gamma E star, right? So this is gamma E star. The evader chooses to play something which is not gamma E star, anything. So it is guaranteed the gamma P star and gamma E star are found out in a way such that the time that we get is less. Why? Because the evader did something stupid. He should not have deviated away from his so-called saddle point or Nash equilibrium strategy, but he chose to deviate for whatever reason. As a result, he got captured in less time. So that is expected because his policy is no longer optimal. His feedback policy is no longer optimal. Similarly, if the pursuer decides to deviate away from his Nash equilibrium policy of gamma P star, the time to capture is going to increase. So it is good for the evader because the pursuer is doing something stupid. So as a result, the time to capture is more. Okay. So this equation is fundamental to the solution of these games. So the question is that this equation can also be written as min max equal to max min. Maybe you have seen such this thing. So min max of t over gamma p gamma e equal to max mean of t. So this equation or this equation are called the saddle point condition or Nash equilibrium, whatever you want to call it. So for this game, for any arbitrary differential game that you come up with, it is not automatic that this equality or the saddle point condition is satisfied, but or such a policy exists over there. It is not very clear, but in this game it can be shown that this is satisfied, and this is well known that this policy for this game this condition is satisfied, and as a result many of the computation becomes easier. Okay, so this can be shown by looking at something called this Hamiltonian. If you know about this, if the Hamiltonian is separable, then this condition is satisfied. This is automatic from optimal control. So I think maybe it was covered in one of these previous lectures, seem like from the headings, but I'm not sure. So yeah, I am not going to talk in too much details about these other techniques, but nonetheless, so this is the saddle point strategies we are looking for. But remember, we are looking for the feedback saddle point strategies, and at the end of the day, I want this feedback saddle point strategies to be implementable, in the sense that I should not be forced to solve complicated nonlinear algebraic equations. I should not be forced to compute for every state value. We should not be able to you should not be forced to compute backward integration of some equations. I should not be forced to compute the solutions of partial differential equations. None of this I want. I want an implementable solution which can be solved for arbitrary initial conditions of the pursuer and evader. And not only that, I would also like to have these solutions in a way that even if the pursuer deviates from his optimal policy, still at every moment the pursuer should be able to calculate what is the optimal policy for him, even when the evader is deviating away from his optimal policy. Let's say we are looking at such a situation where the evader deviates away from the optimal policy, still gamma p star I should be able to compute in a way such that I should be able to achieve this lower time to capture. Okay, so this is sort of the objective of this work. So here, overall objective: derive true feedback solutions, that is, determine control in terms of current states without too much computation. Now, of course, without too much computation is some vague and hand waving terminology. So you might debate endlessly on that. So we can debate, no problem with that, and should be implementable in real time on typical onboard computers. So these two sentences are like very vague. I agree, and we can debate on this. But whatever advantage we can get from efficient computation is what we're looking at. Okay, so I think I should stop now and ask. So was that okay? You want to ask some questions? Are you familiar with the other techniques that are used to solve this sort of problems? Can we get feedback solutions? What's your opinion? Maybe 2-3 questions we can have, if you already have some background on this. Anyone? Hey, what's with the pin drop silence, man? Come on, one of you. Anybody is familiar with this game of two cards or not among the students?
Pin drop silence. Huh?
This is the experience the entire last semester, man.
I think.
Okay, I'll call my name, no problem. Shubhangshu Gupta. What about you?
Yeah, I got to know about these concepts in previous lectures only. So I don't have any much experience, but yeah, I'm understanding well till now.
Okay. Sure. So one way to look at this lecture is to just take it independently, and I will go through some geometric concepts which are very easy to understand, so you can understand one by one whatever is it that we are talking about. But the thing is that the real argument or the real what do you call it point of contention is to compare this with a very well established and very famous established literature that computes also so-called feedback solutions for the game of two cards, and compare the two and try to understand what are the advantages, if any, of this particular method. So anyway, if you don't want the debate, it's okay, but we can maybe later, maybe at the end of the day. Okay. So very short snippets. This is a very long list of existing literature on this. So I'll just give a very quick overview, and you guys can go back and look. Some of these are like so simple that even undergrads, if there are any, can easily understand without any background. And mostly it is geometry. So these Dubin's curves, they're very interesting. So this is a paper by Dubins in 1957. So this Dubin's vehicle, the one that we're talking about, was proposed by him, and the optimal curves. So optimal curves for Dubin vehicles is what? That this is single vehicle with this particular picture that we have now. So left turning radius circle, right turning radius circle, and you want to reach a point with a particular orientation also. So what is the optimal curve to reach this? So in this picture, the one that I drew, it is very simple. It is this one. But suppose you want to reach this point. You want to start from this point and you want to reach this point with this orientation. So that's not so simple, right? So because you might have to go like this and then have a circle and turn around and come like this. And what is the optimal path? Is this the correct way to go? Or should you turn earlier and go like this and then come back and turn like this? If this is the optimal curve as in the shortest path curve. So this Dubin's work, initial work on this was, is very well celebrated. And Dubin's, I think, listed, if I remember correctly, some 26 different types of curves which are optimal. But I think recent papers within the last maybe 5-6 years have brought down the solutions to 6 different types of curves, which characterize all optimal Dubin's curves. But still, many questions I think are unanswered completely. Okay, so this was sort of the start of this thing. And of course, Isaacs, the book that I referred to earlier also, in 1965, he started this entire discussion about differential games. Like I said, this was a army report, classified in 1958 or something, 58, 59, I think he did that work in Rand Corporation. And then this came out in a book later when this was declassified, and a lot of research after that by the Russians and by the Western scientists also. So he did something which is this, maybe you guys are familiar with this HJB, na? Hamilton-Jacobi-Bellman equation. This is a partial differential equation which is used to solve for optimal control problems. So he changed that equation slightly with this min-max formulation. So people call it this Hamilton-Jacobi-Isaacs equations, HJI. Yeah. So HJI is the classical tool for solving this sort of problems. So this is solved for various conditions, various cases, and Isaacs was the one to propose it. But for the game of two cards, Isaacs only solved it for a very special case. So Mars, through a series of papers, I'm not sure this was 71 or 72, so quite a few papers in that time range, he sort of completely solved this game of two cards. But the techniques that were used is this Again, I am not sure. So this barriers, these usable portions, boundary of usable portions, retrogressive path equations, dispersal surfaces, a lot of techniques. Essentially, these names, only if you're familiar, this makes sense. But if you are not familiar, forget about it. But quickly, very roughly speaking, it essentially, so how do I summarize? So it is like you are going to solve this partial differential equation backward from the termination of the game. And in many cases, it can be solved analytically. And if you can solve it analytically, it is possible to sort of divide the state space into small portions, and in each portion you know what is the optimal feedback control for each of these vehicles. But the problem is that this partition depends in some weird way on the directions and the states of the vehicles, and you do not get a true feedback solution. So some computation is involved in finding out these feedback solutions and this partition of the state space. And we feel that this makes it very difficult to implement this in real time as a feedback solution. So of course, this is my claim, and we can debate this if you want. Difficult to implement in real time.
Oh, you are right. In our paper, we have also filled. You might be seen, or I don't know whether you have seen our paper on the game of two cars.
Yeah, I think this one, no, this one is, I think your
Yeah,
paper.
yeah, that paper only. Yes.
Yes.
That
Yeah, we
is-
have seen. Yeah, you have done extensive simulations, I think, and computed
Hmm.
the entire partition very carefully. It was very helpful to have that paper actually.
Okay, so okay, that's so. But this barrier and usable portion, it's very difficult.
Yes, yes.
And understanding first difficult, and then getting feedback solution. I think it's hello. Yeah.
Yes, yes.
Hmm.
So what this army guys were doing, I think until a few years ago in the US, was that they were computing these barrier surfaces and they were computing the this dispersal surface and the universal surface. I have written this, I haven't written. So this they're computing this for each theta. So this is like the angle difference between the two. They are computing this, and they were just doing it for all. So they discretize this theta and they compute these universal surfaces for all of them, and they just store it somewhere. So when a real situation comes, they just interpolate between the two and sort of pick out what is the corresponding EDS and US for the particular situation that they are facing, and from there they construct the feedback. This is doable, I guess, right now. Right now, with the computation that we have in our hands, it is doable. But we were looking for a true feedback. So luckily, why we thought it's possible is because these guys, this Jacobo, Ruiz, and some other people, they have done exactly the same thing. So this is a true feedback they have been able to find out for the homicidal chauffeur game. So homicidal chauffeur, again, for the students, it is like the same problem. So you have one car with these turning constraints. So it cannot go into these circles, and it is sort of facing like this. But the target, the other car, the evader, this one is like a simple motion. So it has no turning constraints. So it can go, it can change directions immediately. It can go anywhere. So this is called a homicidal chauffeur because it's like somebody is driving a car. So this is like the car, and some chauffeur is driving this car who wants to kill this guy, this evader. And this evader is like a person. So typically the velocity for this evader is assumed to be smaller than the velocity of this car, but because he can turn instantly, he can avoid being run over in quite a lot of cases. So this homicidal chauffeur is also very interesting. This was also proposed in Isaacs only, and this Jacobo could find out the true feedback solution in that case.
I think this is like this problem is famous in the Lady in the Lake, Lion, and the so different name, right?
There are many different problems. All of these proposed by Isaacs.
They have given the nice name also.
Yes, very nice name. Yes. yeah. Lion is actually one of the most interesting problems because the moment you put in an arena, it is even more difficult to solve.
Yes, that closed domain.
Yeah, closed domain. Yeah. So, so then at this point we were thinking, okay, we should be able to find out something which is reasonable geometrically. And actually quite a lot of work has been done by this guy, Cockayne in 1967, 68, 69, in that time range. So they have calculated what are known as this reachability sets. So pardon me, this reachable sets and reachability sets I mix up, I think, through this presentation. So you just consider them the same. So this reachable sets or reachability sets of Dubin's vehicles. So they introduced, not introduced, I mean, people knew about reachable sets for a long time, but they used the reachable sets for Dubin's vehicles for solving, at least not really solving the game, but at least finding out some conditions for capture. So this they did for some time. And this guys also did something similar in 94. So it seemed like this area is sort of getting filled up. So we thought that, okay, we should have a look. And Siothras and some of his students also have tried to use this reachability sets for solving some of these games in recent times.
That is a Georgia Tech, right?
Yes, yes,
Hmm.
yes. Siothras, I should have written.
Siothras, yes, Siothras.
Yes, but these guys also are not really looking at this game of two cars too carefully. So, so that's the summary. So yeah, let's see if maybe by next time you can look up some of these things and we can have a little bit more discussion about the background. But let us talk about our stuff.
So
Okay.
just you start. I have a question. Maybe like because I think so. This reachability is just a kind of it's a like I don't know. So it's the inverse of this dynamic programming type things, right?
No, dynamic programming type thing.
So when say dynamic programming, what you do, or maybe I should not say dynamic programming. See, when you have a target point and then you do the inverse simulation, right? Huh? So
Yes.
that is one approach. Whatever the like you have you are going to intercept, okay,
Yes.
and then you do the backward simulations. But in the reachability now you are doing the forward simulation and you look where can you go all level, right?
Yes, yes, yes. That way it is inverse. Yes, yes.
Yes.
Very nice insight. Yeah, that's correct. It is like reverse in that sense. Yes.
So
Yes.
so and then this opens totally to different domain.
Yes, I mean the utilities we you judge at the end of the talk. I am very hopeful, but then it's not that we have been able to solve all the issues completely. So you please judge at the end of the day how useful this approach is. But we feel like this can lead to something realistic solutions for many of these games that all of us are interested in, like this multiplayer pursuit evasion, multiple pursuers, one evader. So all these problems was like so difficult to solve if you use the HJI, the backward integration method. Whereas if you look at the forward integration or forward time technique that we are going to use, maybe it will come down to something which is tractable, something that we can find a solution to. So that's the hope. But it's still hope. We have not been able to solve it completely. So that I should say a priori. So before we begin the math, what have we achieved? I want to tell, in the sense that after I do all the math, after I write down all the theorems, I do some of the proofs. I don't know. I'm really going too slow, maybe. But if I do all this stuff, so at the end of the day, what is it that you have to do as an engineer? You come and what is it that you have to do to find out the feedback solution? So let me say that. So this is without any explanation, just what to do, not how. Okay. So let me try to explain this. So what you have to do in our method, the method that we are going to tell you over the next 1.5 hours or something, is that you have this evader over here pointed this way, and you have this pursuer over here pointed this way, and you have these two circles, right, for the pursuer, and you have these two circles for the evader. So this is not at the initial condition. This is true for every time in the game, right? So as the game is played on, you will always have some orientation of the evader. You will always have some orientation of the pursuer, and you will have these two circles, a pair of circles for the pursuer and the evader both. So what our method tells us to do, and why will come later, I'm just saying what to do, is that you calculate the common tangents for all this pair of circles. So as you can understand, suppose I call this circle 1, circle 2, circle 3, circle 4. So you have all these combinations 1, 3, 1, 4, 2, 3, 2, 4. You have all these circle combinations, and for each such pair, let's say 1, 3 ke liye, we have these 4 common tangents that are possible. Similarly, for 2, 3, there will be 4 common tangents. 1, 4, there'll be 4 common tangents and so on. So 16 tangents in all. Yeah, 16 common tangents total possible. So there is a simple logic. You don't have to do any computation, just very simple logic, a simple trick, which we'll tell later. Let's not go into that now. But we have to look at only 4 tangents, 1 per pair. So essentially, it is sort of so easy. You can do it right now, but let's postpone that. We don't require this once. Only this common tangent is what that we have to worry about for this pair, 1, 3 pair. So 1, 3 pair ke liye we have this 1 common tangent. For 2, 4 pair, again we will have some other common tangent. So this way we'll have 4 common tangents which we are interested in. What to do with that, I'll tell. So we have 4 common tangents in the end after we do this simple trick. So after that, what we do is that we decide which one is the correct common tangent based on something. So out of these 4, we have to pick one. So the promise is that after we do this picking, I'll explain how I pick this common tangent. Suppose after I do all these computations, whatever I have here, after I explain this, after that, suppose I pick this common tangent, 1, 3 wala common tangent. Of course, my computation might tell me that the 2, 4 wala common tangent is what I should worry about, or let's say the 1, 3 or 1, 4 wala common tangent that I should worry about. I do not know, but somehow or the other I pick one of them. Let's say, for the sake of easy drawing, that I pick this, the blue one that I have marked over here. I pick this common tangent somehow. So after that, the optimal play is very simple. Optimal play is that the evader should also proceed on this common tangent, and the pursuer should also proceed along this common tangent. So evader should go like this, and the pursuer starting from here, it should go like this and proceed along this common tangent, and the capture will happen somewhere over here. Okay, so this is how it works. So after all the math that we'll show for a long time, at the end of the day, this is how it works. So essentially, you have to just find these 4 common tangents for all this pair of circles, and out of which you have to pick one. I'll tell you how in just 1 more minute. But after I pick this common tangent, I just proceed along that common tangent. Of course, to reach that common tangent, I might have to go a bit along this minimum radius turning circle. So I go along that, and like this one. So for example, the pursuer was here. To reach this common tangent, I have to proceed along this circle and come here. That is okay. That is your optimal path. And after that, you proceed along this common tangent. And then at the end of the day, both the pursuer and the evader on a line of sight track, and you end up just catching them just one behind the other, and they just intersect after some time, because the pursuer is faster than the evader. So capture occurs somewhere along this common tangent. So this is the promise, and this is what we prove. And what about which common tangent to pick? Isn't that not dependent somehow on a lot of computation? So this common tangent is picked in a strange way. So what we do is that we know this common tangent, right? So 1, 3 ke liye we have this common tangent. For 2, 4 we have this common tangent. For 2, 3 we'll have some common tangent like this. So you come like this and you go like this. So some common tangent like this. So this way we have common tangents for each one of them, and I capture that if I follow this path, I just calculate, sorry, not capture, I just calculate. If I follow this path, so this, let's say this is path 1, this is path 2, this is path 3, and path 4 similarly. For each of these paths, what is the time to capture? Okay, so in this table, I make a table and I just put these values. So this plus is like you first use the this turning circle for the evader, and for pursuer use the right turn. You also use the left turning circle. So this one and this one. The time taken if you go along this one and you go along this one, and the common tangent to those, if you do, then what is the time taken, that you calculate. So this is this value. And similarly for the other common tangents, you find out the values. Values means what? The time taken to capture if you proceed along those paths. So you write down all these values, and then what you do is that at each instant you just solve this 2x2 matrix game. So are you familiar with this 2x2 matrix game? It is not very hard anyway. It's just like a, you have to just check for this one. If you fix at this one, what is the min max? what is the min max? If you fix at this one, what is the max? If you fix at this one, what is the max? And you choose the minimum of the two. This is like, just comparing two values. So that's all the computation you have to do in real time. Okay. So of course, to compute the time taken along this common tangents, you must know the orientation of the pursuer. You need to know the orientation of the evader, and you also need to know what is the difference in the states of these two. So that's where you use the current information, the state information. Like I said, long ago I said, remember that you must know the. We are looking at true feedback, means that we should use. I don't know where I wrote. You must use the state values of the pursuer and the evader both. So yeah, here. So use these values and calculate the common tangents and the time taken along the common tangents, and that's all you need to do. So at each instant you have to do this, and this can be done by closed form formulas. You can calculate closed form equations of this TAA, TCA, whatever, TAC. This is like just some notation. I haven't introduced it completely, but I just want to give you a flavor before I start. So this is just computing this 4 times and creating this table at each instant and finding out what is the min max of this 2x2 finite matrix game. Okay, and if you use that, so suppose it turns out what is the min max. So suppose you turn out this is the min max. So you choose out of the 4 paths, you choose that common tangent. So you proceed so that the game is played along that common tangent. The next discretization interval, if you implementing this, again you do this computation and again you choose the correct one. So the evader plays non-optimally, no problem. You just do this computation and pick the min max according to this finite matrix game. And the guarantee here in our method is that this method actually gives you the true differential equation, differential game curve feedback solution, the Nash equilibrium solution that we're looking for. You can compute this way only for this situation. Situation is what? Large initial separation, Vp greater than Ve, omega p greater than omega e. Under this simplifying assumptions, this is a true feedback. That is our claim. Okay. I don't expect you to understand completely. We'll go through this slowly, but just in case, this is just to give you some idea about how to use this. Any questions?
So I don't know, student has question, but I just want to. So I think the way you have formulated the problem, you have bring down to like a Nash equilibrium type table, right?
Yes. Yes.
And
So
then
Nash
what?
equilibrium, yes, Nash equilibrium will be there. There is a guarantee, and this finite Nash equilibrium corresponds to the true feedback Nash equilibrium also.
And then you have what this table has. See the way you have decomposed the problems. If one is like, say you have taken the extreme, both the min and max things, what they can do best or worst.
Yes.
To this using the tangent and minimum turn radius constraint. So this is you are finding the path and like finding the like set of path. And once you have a set of path, you just have to compute your control command. That because from Dubins or anything we know that, right?
The control command is like control command is automatic, no? Because if suppose our optimization here in this min max game solution tells you that 1 and 3 is the optimal thing. So 1 means that you know that this is like plus omega m for this guy.
Yes, that CLC, yeah. What I was telling that, na, CLC or LCL, clockwise or anti-clockwise.
Yes,
like
yes.
That way, so that sequence will give, because you may have to come to the one circle and then straight path and then again, na?
Yes.
So is this way or I don't know, I am jumping?
No, it's correct. That's all you need to do. But why this is true is what I'm going to explain. But I'm not sure how much I can explain. But yeah, this is the end product. So I was just showing you the end product before I start the discussion, because the discussion will go on about reachability sets, and people will lose track of what is it that we're going to achieve at the end. So I just thought that I'll show the end product before I start with the math. So this is the end product, that there is a guarantee that if you do this, you are going to play optimally.
Sir, I have one question. Is the optimal is unique or it's not unique for this case?
That's a very difficult question. Are you asking it out of the blue, or you know this already? I want to know.
No, I don't know.
Yeah. So you see, there are some cases. So this is like a very interesting question. So normally speaking, in most situation, it will be unique. But some cases may there is this thing called this dispersal surfaces. So this is studied widely, in which there are these two choices, and these two choices give you the same time to go. So this at that point exactly, both are undecided. You can go turn right, you can turn left, both will lead to the same kind of capture. But the moment one of these guys take a decision in one direction, then it is fixed. So mathematically speaking, it is not unique, but practically speaking, the moment one of them takes a decision to go right or left, it is fixed. So you are out of the dispersal surface. So dispersal surface is like a one-dimensional or two-dimensional manifold. If you look at the reduced, forget about it. Don't worry about that dimension. But it is like a very narrow region. So you don't really need to worry about the dispersal surface in most practical situations. But mathematically speaking, yeah, it is not unique all the time. In some cases, and some examples I think I have, in which you can turn right or left, both will lead to equal time. So that decision nobody can make. You can take your call. It's like, so people say use randomized strategies over there, but either way it's the same thing. You are out of the dispersal surface next instant. Instant means if you are discretizing this game at the end of the day, any implementation will require to discretize, right? So you are out of that surface, and then the min-max policy or the max-min policy again becomes unique. Okay. So it's a very easy example of that. Don't mute yourself. That was a very good question. Who was it?
Yeah. Sorry. Sorry, my.
Dekho. So I'll tell you. Huh? So suppose this guy is pointing like this, and this guy is pointing like this. Yeah. So
Okay.
okay, let me not. I think it's like 9:04 already. So let me have this discussion next time, because this lists too many interesting questions. I'll bring it up next time. I remember, huh? And then we can have a good discussion about this dispersal surfaces. So the decisions are always not unique. You can try to construct also next time. So I'll just take 5 more minutes to quickly talk about this thing. And I don't know, probably we should stop, because you said 1 hour. I'm already
So
beyond.
so maybe like interested people are there. So maybe another 5 minutes you can wrap up and we'll start tomorrow again.
Yes.
Okay. So anyway, I am interested. I will. It's a anyway for obvious reason I am interested.
Yes. I know you have worked in this area also, and yeah, sure.
Yeah.
So this, so the approach we will do is sort of written out here. So firstly, reachability sets, because some of you might be not familiar with reachability sets of Dubin's vehicles. So we will give some examples. So reachability set, whether containment of reachability set of the evader by the reachability set of the pursuer is enough for capture or not, that we will study through few counter examples. So introduce something, this construction, this continuous subsets of reachability sets is our construction. So this seems to be a vital link in our understanding of optimal capture using geometry, which was missing. So this I want to say. This proves, I do not know, another 1 hour may hoga ke nahi, but I'll try to sort of say something, that continuous containment is a necessary sufficient condition for capture. This I'll try to sort of show, and then show that capture occurs at the boundaries of some special continuous subsets. So all these constructions are required to do what? At the end of the day, I want to have a guarantee, what Professor Kothari was just now saying, na, that look, this is a CS type. So CS means what? A circle and straight line type trajectories are optimal for this case, always. So to prove this CS type, I require all the steps through reachability sets. Okay, and independently also reachability sets are interesting, because it provides a lot of insight into the solution of the game. And then once we have the CS type guarantee for these games, at the time we use the CS type and the geometry that we have, we use along with some Euler-Lagrange equations. We don't use it for computation, just for proof. We show that common tangents, the one that I said initially, these common tangents are all that we need to look at. We don't need to look at any other types of curves at all in this game. And once we have these common tangents, using geometry of these common tangents, we're going to form this 2x2 matrix game that I showed earlier. So I'll try my best, but I am not sure whether how long this will take to do, but at least some idea. of this I will do. So what you can do is that if you are interested, there are only some few guys. So if you're interested, you can download some of these papers. This most of this work is in this one. This is coming out in this transactions and automatic control, but is not out yet. But there's an archive version available, so you can download and keep if you want to refer to it during the lecture. And some of these computations, say this 2x2 matrix games, those things are there in this ECC paper earlier. So we could not fit this into this paper because it is already too long. So you might have to refer to this one also. CDC paper is a subset of this third one. So that this one you don't need. So if you are really interested and you want to know and want to take it further, whatever, so I would suggest that you can download this archive version and sort of keep it as a reference in case something comes up which requires further discussion. Okay. So after that, we start with the reachability set discussion. This we can take up, I think, tomorrow. Okay.
Okay. So
Any